So in this video, we're going to continue on looking at the reaction of alkenes with a particular focus on the electrophilic addition reactions of alkenes. So just a quick recap from our last video, we saw that alkenes contain carbon-carbon double bonds, and that means they contain this region of high electron density around that carbon-carbon double bond, because you've got two pairs of electrons there. One of those bonds within the carbon-carbon double bond is a sigma bond, but one is a pi bond, which is slightly weaker, and it's prone to attack by what we call electrophiles, molecules that love electrons, that are attracted to regions of high electron density. And so as a result, we see that alkenes undergo these type of reactions called electrophilic addition reactions. And that's where we're going to be adding a molecule across the double bond. So in this video, we're going to have a closer look at the reaction mechanism and what actually happens in terms of the movement of electrons in these reactions. So let's take a look at the mechanism of this type of reaction of alkenes, this reaction of electrophilic addition. Remember that a mechanism is just essentially a sequence of steps in a reaction. It outlines each step of a reaction and essentially what happens to the electrons within a reaction. Why is the reaction proceeding? What direction do the electrons go? Where do they move from and to, and so on. You'll see that this mechanism is quite different to the one that we saw with the photochemical substitution of alkenes. This is quite a different mechanism and will even involve a different type of arrow than in that mechanism. But this mechanism will be more similar to ones that we'll see in future topics, including at A2. So it's important that we get our heads around these and we get into good habits with how to draw these mechanisms and understand what's happening with them. So let's chat through briefly the mechanism, and then really I think it's easier to see with an example. So the first thing that happens is the electrophile. Remember, that's a molecule or a group of atoms that have either a full positive charge or a partial positive charge. So the electrophile, which has some positive character, is attracted to the carbon-carbon double bond, since this is a region of high electron density. Then what happens is the electrons in the pi bond, they come out and actually form a bond to the positive end of the electrophile. So here the pi bond is broken and a new bond is formed to the positive end of the electrophile. So a bond is broken and a bond is made with a pair of electrons that were originally in the pi bond of the carbon-carbon double bond. Let's imagine our electrophile is a hydrogen halide, like we saw as one of our examples on the previous page, with the hydrogen being slightly positive and the halide ion, or the halogen atom within that molecule, being slightly negative. So the pi bond is breaking and forming a bond with the delta positive hydrogen, and essentially that's forming a bond with the hydrogen. And we know that hydrogen can only form one bond because it can only have two electrons in its orbital, and that brings us on to step number 3. Because it can only have two electrons in its orbital, its other bond breaks heterolytically. In other words, both of the shared electrons go to one atom. In other words, that bond between hydrogen and X, whatever X is, be it chlorine, bromine, iodine, or whatever, that breaks. So that's step number 3. So step number 3 is saying that when that bond is formed with hydrogen, between the carbon of the double bond and hydrogen, then this bond will break heterolytically, and we represent that by a double-headed arrow, in other words a normal arrow, and a curly one at that, that bond breaks and those electrons both go essentially to the X atom, and that then becomes an X ion, X minus. So here we're seeing heterolytic fission, heterolytic breaking of the bond, and that means that both of the shared electrons go to one atom. Previously we saw with homolytic fission that when the bond breaks, that one electron goes to each of the atoms in the shared bond. So as a result of this, the hydrogen attaches to one of the carbon atoms by a sigma bond, and the other end of the electrophile becomes a negatively charged ion, X minus, as we've already seen. The other carbon atom, and that's of the double bond, has lost a share of electrons, and so a positively charged carbon ion is formed, and we call that a carbocation. The carbo bit obviously referring to carbon, cation meaning a positively charged ion. So we call that a carbocation. That's a term that we'll use in a lot of the topics to come. And the carbocation attracts the negative ion of the original electrophile, in other words, X-. And the X- ion can essentially use the electron pair that it got from the breaking of the HX bond to form a bond with that carbocation. So again, it uses that pair of electrons that it got from the breaking of HX to form a bond with the carbocation. And again, that will be another sigma bond being formed between carbon and whatever X is. So let's have a look at actually what that mechanism looks like in practice. And just a reminder that in a reaction mechanism, an arrow represents the direction of a movement of a pair of electrons. And it's a curly arrow that we draw, something like this. And because it's a double-headed arrow, that means it's showing the movement of a pair of electrons. And then just a brief note underneath to summarise this general mechanism and a general equation. And the alkenes undergo this type of reaction because they possess an unsaturated functional group, in other words, our carbon-carbon double bond, which can undergo electrophilic addition, in other words, the addition of an electrophile across that double bond to give a saturated product. So our carbons in the final product will have just single bonds. So let's show the general equation for this type of reaction, and we'll just use ethene as our example of the alkene. So ethene has 2 carbons with a double bond between them, and a total of 4 hydrogens, 2 on each carbon atom. And let's say that reacts with a general electrophile, which we'll call XY. That will then essentially add across the double bond. So the pi bond of your carbon-carbon double bond will break, and so we'll be left with just the sigma bond, which is a single bond. And the X of our electrophile will add to one carbon atom, and the Y of our electrophile will add to the other carbon atom. And so what we can see is that we've started off with an unsaturated reactant due to the presence of that carbon-carbon double bond, and our product is then saturated. It only has single bonds in it. We say the carbon atoms are completely saturated. So you can see overall the story is quite simple. We start with an alkene and we have an electrophile, and if we break that electrophile up into 2 parts, the positive end and the more negative end, then that essentially splits up and adds across the double bond. And what we mean by that is that the positive part will attach to one carbon atom, and the negative part of the electrophile will, or the partially negative part, will add to the other carbon atom. But let's see what happens in terms of the movement of our electrons. So let's have a look at an example of one of these mechanisms of the electrophilic addition of alkenes. So we'll look at the reaction first of all of ethene with hydrogen bromide. The mechanism or the steps in this reaction are described at the bottom half of the page. But we're going to draw the mechanism, and you have to be able to draw these mechanisms as part of this topic, which is point 8 on the specification of this topic. In this first example, I am going to draw in some of the electron pairs just so that you can see the movement of electrons, where they actually go during this reaction and during this mechanism. But in the exam, you don't have to draw all the electron pairs. I'll show you which ones you do have to do. But for this example, just so we can see the actual movement of electrons, then we'll draw them in. So we'll start with a molecule of ethene. So we've drawn that with the bonds there. And I'm also going to draw in the electron pairs in this carbon-carbon double bond. So the sigma bond I'm going to represent with a pink pair of electrons. You can colour it whatever you like, or not colour-coded if you wish, but I just find colour coding helpful in sort of tracking where the electrons have gone. And then the pi bond of that carbon-carbon double bond, I'm going to show in green electrons. And down below ethene, I'm going to draw our hydrogen bromide. So it's HBr, and that is bonded together with a single covalent bond. So again, you can see a shared pair of electrons there as well. And in these mechanisms, it's important to draw your delta charges on the electrophile. So it's our hydrogen that is slightly positive and our bromine that is slightly negative. And that's why it is attracted to the ethene. It's attracted to the centre of it, this region of high electron density, the carbon-carbon double bond, where we have two electron pairs quite close together. So the partially positive end, the hydrogen end, is attracted to the carbon-carbon double bond. And that's essentially step number 1, where the positive end of the electrophile is attracted to the carbon-carbon double bond. And this is what we know as electrophilic attack. The slightly positive hydrogen is what we call electron deficient, and so it's attracted to the region of high electron density, and it essentially wants those electrons. And so that's the first thing that happens. So once the electrophile has moved in close towards the carbon-carbon double bond, an electron pair from the pi bond of the double bond is used to form a bond with the hydrogen atom of the electrophile of the hydrogen bromide. So that green pair of electrons as such, that bond, the pi bond of the carbon-carbon double bond breaks, and that electron pair is used to form a bond with the hydrogen. As a result, the hydrogen-bromine bond breaks as well. Why does that happen? Well, because hydrogen can only have one bond. It can only have 2 electrons in its outer shell. And so the hydrogen-bromine bond breaks, and it breaks heterolytically. And so what that means is that this electron pair that was originally shared between hydrogen and bromine now moves towards the bromine completely. The bromine atom takes both of those electrons. So that's what we mean by heterolytically. It breaks in such a way that one of the atoms of the shared bond leaves with both of the electrons. So that's how we represent the first couple of stages of this mechanism with a diagram and with these curly arrows. It's described down below what we've just talked through. So if you wanted to kind of number it in terms of the steps that are written down below, the first step describes how the electrophile moves in towards the carbon-carbon double bond, and the second step describes how that electron pair from the carbon-carbon double bond is used to form a bond between the carbon and the hydrogen, and then how the hydrogen-bromine bond breaks heterolytically so that the bromine runs away with both of the electrons from that electron pair. So what do we get as a result? Well, let's draw the kind of backbone of our organic molecule. We now have our carbon-carbon bond, but now it's just a single bond with that pink pair of electrons from the original bond. That would have been the original sigma bond. It's the pi bond that has broken. The sigma bond is still intact. We haven't done anything to our hydrogens, so we'll just draw them on like this. And let's think about what bonds have formed now. So in this case, it doesn't matter which carbon atom you draw it on, but I'll draw it on the one on the left. The bond that has formed is between a carbon atom and the hydrogen atom of the electrophile. And how we form that bond is with the electrons from the original pi bond of the carbon-carbon double bond. And I'm just representing that by using green electrons so that you can show what electrons have been used to form that bond. But as a result of the pi bond of the original carbon-carbon double bond breaking, the other carbon has lost its share of electrons. And so the other carbon ends up being positively charged. We call it a carbocation. So you need to represent that by showing a positive sign by the other carbon atom. What else did we form in the first step? Well, if you remember, the hydrogen-bromine bond broke heterolytically, and the bromine atom escaped with both of those electrons from the original hydrogen-bromine bond, and that will be negatively charged because it essentially gained an electron. And so it is negatively charged. And a way to check is that each stage of your mechanism should have the same overall charge in it. So you can see in the first step, there were no charges, no full charges. And now here in the second stage, we have our positive carbon carbocation, and we have our negative bromide ion. So hopefully you can see what's going to happen now. The positive carbocation essentially attracts the negative bromide ion, and a bond is formed between the two. But what we need to remember is that the curly arrows in a mechanism represent the direction of the movement of electrons. So we need to think about, how does that bond form? We need one shared pair of electrons for a covalent bond to form. So essentially that bond forms from those purple electrons in our diagram, and the electrons that are currently with the bromide ion. So while we might think that the bond forms between the carbon and the bromide ion, we need to show the direction of the movement of electrons, and so we show it from the bromide ion into the carbocation, because the carbocation has no electrons to donate towards this bond, and the electrons move from the bromide ion towards the carbon, and that pair of electrons that are currently with the bromide ion are now shared between the carbon and the bromine atom. And to match it up with the statements below, that is step number 3 of our description. So the last thing to do to complete the mechanism is to draw our final product. So we'll start with what we had in the previous step. So we had our carbon-carbon single bond, and that was our sigma bond, which we represented with our pink pair of electrons. And then we'll draw our hydrogens around that, which just came from the original ethene molecule. And then what we also had in our previous step was the carbon bonded to the hydrogen, which came from the electrophile. We represented that with a green pair of electrons. And then now what we formed is a bond between our carbon and our bromine, and we formed that with the purple pair of electrons. So if you were asked to draw this in an exam, you wouldn't have to colour code it. You wouldn't have to show all of these electron pairs. You do have to show the lone pair on the bromide ion here. But we'll do that in our next example. But I think the electron pairs at this stage are helpful in helping you see where those electrons come from, where the bonds break, and where the bonds are formed between two different atoms. Again, check at this stage that your charges are balanced in your final step. You can see that we have no charge in the final step or stage of this mechanism, and therefore the charge is balanced throughout. The total charge at each stage of the mechanism is equal to 0. There's no charges in the first step, in the first stage, and there are one positive and one negative in the second step, and so they cancel out to give 0, and there's no charges in our final step. If we were to give our final molecule a name, it would be called bromoethane. So you can write that above that if you wish. So that is the mechanism for the electrophilic addition of ethene with hydrogen bromide. And you can see that even though the alkene might change, even though the electrophile might change, the actual format of the mechanism is exactly the same each time. It's something you need to be confident in drawing. Again, obviously you won't be examined on it at this stage, but you'll see very similar mechanisms when you come on to A2. So it is important that you understand these and the movement of electrons and are able to draw these. So what I would recommend you doing is taking a file page perhaps, studying this mechanism and seeing if you can redraw it. And we're going to have a look at one more example together, then there's 2 more for you to do in your notes anyway. But it would be good to practice drawing this even, read through your notes, read through the step 1, 2 and 3 down below as you draw the mechanism to make sure you understand what are these arrows representing and what's happening at each stage of the mechanism. Let's now look at another example of this reaction, the electrophilic addition, again of ethene but this time with bromine. So rather than hydrogen bromide with bromine. So the 4 reactions that are mentioned of this type on your specification are with chlorine, bromine, hydrogen bromide and hydrogen chloride. So we've looked at hydrogen bromide. Let's now look at bromine. So the equation has been written there for you, and you can see that we are starting with 2 reactants, ethene and bromine, and we form just one product. And that tells us that this is an addition reaction. One molecule is simply being added to another. It's not a substitution. There's no molecule being removed from the original reactant. The bromine is simply adding on to the ethene molecule. So let's have a look at the structural equation. So we start off with ethene, which has the formula C2H4, a carbon-carbon double bond, and each carbon being attached then to 2 hydrogens as well. That reacts with bromine, which is a red-brown liquid. And we see, just as with hydrogen bromide, that the bromine adds across the carbon-carbon double bond. So you can see there from the formula of bromine, Br2, there's 2 bromine atoms covalently bonded together, and 1 atom will add to each of the carbon atoms, leaving a single bond between the 2 carbon atoms rather than the original double bond. This molecule, if we think about its name, the longest chain is 2 carbons, so it's going to be ethane. The ending now changes to ethane because there's no double bonds anymore, but we need to name our substituents as well, and they would be on carbon 1 and carbon 2. So we name this 1, 2 dibromoethane. And actually that molecule would be colourless. And that's actually the test for alkenes, which we'll look at in just a second. So the colour of bromine would disappear. So let's have a look now at the mechanism, and then we will talk a little bit about why this is a little bit surprising, a little bit strange. So what I want you to see with this mechanism is that it's essentially identical to the mechanism we drew in the previous page, but with just a different example of an electrophile. So first of all, draw your ethene. And this time I'm not going to draw all the electron pairs that we need in this. I'm just going to draw the ones that are necessary. Hopefully now from the previous example you have an idea of how the electrons move and where they move from and to. But in this case I'm just going to draw the mechanism as you would be required to in an exam situation. So I'm going to still do a little bit of colour coding with the electrophile just so that you can see where the atoms go, especially because we're talking about 2 bromine atoms. So again, I would normally draw my electrophile kind of in a vertical way so that we can represent our mechanism. It's fine if you do it kind of across the way, but just make sure your curly arrows represent the same motion, the same movement of electrons. So the end that will be attracted to the ethene molecule is the delta positive end, and we'll draw the delta negative end down at the bottom. Now, what you might say to me, and you'd be absolutely right, is that bromine is a non-polar molecule. So why are we writing delta charges in this? Well, if you pause that thought for a second, we'll talk about it in a wee minute. So yes, bromine is non-polar. And so it's quite surprising, as it says below, that it should act as an electrophile. But we'll talk about that in one wee second. So again, with our mechanism, just as we saw before, the first step that happens is, well, the electrophile approaches the carbon-carbon double bond because it's a region of high electron density. So the delta positive end of your electrophile is attracted to the double bond because it's a region of high electron density. And this time what we do is we just draw a curly arrow from our double bond to the positive end of our bromine molecule, so the first bromine atom. This time we're not drawing a pair of electrons in, but remember what is happening here. Essentially, the electrons from the pi bond of the double bond are being used to form a bond with the bromine. So a bond between one of the carbon atoms with the bromine. And as a result, the bromine can't have another bond. It can't have an extra bond. So what happens is the electrons in this bond move to the other bromine atom. So this bond breaks heterolytically, where the electron pair goes to that other bromine atom. So that's the first step done, where the electrophile approaches the double bond, and then the electrons from the pi bond of the double bond are used to form a bond with the bromine at the delta positive end, and then the bromine bond breaks, and the electrons move towards the other bromine atom. So what are we then left with? Well, the carbon bond is now just a single bond. And we'll draw the original hydrogens on it. And you can draw, again, the bromine on either carbon atom in this case. It doesn't matter because this alkene is what we call symmetrical. We'll talk about how that can differ in later examples. So I'm just going to add it to the carbon on the left as we have done in previous examples. Remember that the other carbon atom is now essentially short an electron, because the double bond has broken, and it's lost its share of that pair of electrons, and so therefore there's a positive charge. Remember, the loss of an electron causes a positive charge. What else do we have? Well, we also have our bromide ion. So that purple bromine atom escaped with the pair of electrons from the bromine-bromine bond. And so that now acts as a lone pair. So this is an electron pair that we do have to draw in. And then we also have to draw our negative charge as well. You don't have to draw a circle around it. You can just write Br minus. I normally do that just as 2 dots because it's essentially acting as a lone pair, and that's the way you would normally see it in a mark scheme. And then what happens at this stage? So that's what we've produced from the first step, from the double bond breaking, forming a bond with the green bromine atom, and that bromine-bromine bond breaking. What happens now? Well, you can see we've got a positive and a negative charge, and those are attracted to each other. And a really common mistake, please don't draw this in because this is a mistake, is for people to do the arrow like this, because they say, oh, well, carbon's forming a bond with bromine. And yes, it is. But what you've got to remember is that this arrow must show the direction of the electron. So instead of doing that, what we want to do is draw the arrow this way, because the bromide ion is using its lone pair of electrons that it got from the first step of the bromine-bromine bond breaking heterolytically. It's using that pair of electrons to form a bond with the carbocation. So then a bond is formed between carbon and bromine. So all that's left to do is draw our final product. So let's draw what we originally had, our carbon, 2 carbons, 4 hydrogens in total, and then our bromines. Again, in an exam you wouldn't have to colour code, but just to show where this has come from in the different stages of this mechanism. And as you can see, the charges at each stage of the mechanism are balanced. No full charges in the first step. We have 1 positive and 1 negative, which cancel in the second step, and then no charges overall in the third step. So please do check that. So you can see this time we haven't drawn all the electron pairs. Can I just highlight, you don't need to necessarily do this, but what you do need to include in your mechanisms, these delta charges, so your delta positive and your delta minus. You need to include obviously your curly arrows. You need to include the positive charge in the carbocation, the negative charge in the bromide ion, and you need to include the lone pair of electrons that has kind of broken away from your electrophile, and that curly arrow as well. The other electron pairs you do not have to do, the ones that we would have done in our first example, but you must include those delta charges, the full charges in the second step, and the lone pair of your electrons. So that's your mechanism. You can see that it is literally identical to the previous example, but with just a different electrophile. So get into the habit of drawing it exactly like that, so that you could repeat that in a test. Now, as we said, as we started this example, it is quite surprising that bromine acts in this way, that this reaction happens, because bromine is a non-polar molecule. And what we said with our electrophiles is that our electrophiles must be molecules that have either a full positive charge or a partial positive charge. Well, there's a couple of things that allow this reaction to proceed, even though bromine is non-polar. So because bromine is non-polar, the 2 bromine atoms have equal share of that pair of electrons in the covalent bond. They're obviously identical atoms, and so they have the same pull on the electrons. They have the same electronegativity. But as the bromine molecule approaches the carbon-carbon double bond in the alkene, that region of high electron density, and in particular the electrons in the pi orbital of the carbon-carbon double bond, will start to repel the shared pair of electrons in the bromine-bromine bond. Remember that electrons are all negatively charged, and so they repel each other. And so therefore, as the bromine approaches these electrons start to repel those electrons in the bromine-bromine bond. And so they start to move closer to the kind of furthest away bromine atom. So imagine the bromine molecule approaching the carbon-carbon double bond, and then there being repulsion from the electrons within the pi orbital, and that essentially pushes the electrons further away from the closer bromine atom and towards the bromine atom that's further away, because the electrons are repelling that shared pair of electrons. So what do we get as a result? Well, you can see in the second diagram here on the right hand side, the electron pair is now nearer one end of the bromine molecule, so it's closer to that second bromine atom. You can see it's now an uneven distribution of the electron pair. It's closer to the purple bromine atom, and so that makes that end delta negative because it has a greater share of the electron pair, and it makes the green bromine atom delta positive because it has less of a share of the electrons. Therefore, since we have a partial charge now, this molecule is now essentially temporarily polar. Then we can call this an electrophile, and it's ready to act as an electrophile. Essentially, it's ready to do electrophilic addition. So that's the first thing, that as the non-polar bromine molecule approaches the carbon-carbon double bond, we'll see repulsion of the electrons from the region of high electron density of the carbon-carbon double bond, and it will repel that pair of electrons in the bromine-bromine bond, and therefore pushing it closer to one end of the bromine molecule than the other, and therefore causing the molecule to be polar. The other thing that happens is mentioned down at the bottom here about molecular vibrations. So you'll know that instantaneous dipoles can arise just simply by molecular vibrations. So if we start off with our non-polar bromine molecule, where the electron pair sits exactly in the middle of those two bromine atoms, it's shared equally by the two bromine atoms within that covalent bond, and we say the molecule is non-polar, and the electron cloud is essentially evenly distributed across that molecule. But what can happen is the molecule can start to vibrate, which can cause the electrons to move, and in a certain instant, if we were to take a snapshot, that could vibrate in such a way that pushes the electrons closer to the purple bromine atom, that end of the molecule. What do we end up with then? Well, then we end up with an uneven distribution of that electron cloud. You can see the electrons are sitting slightly closer to the purple bromine atom now. So there's less electron density around the green bromine atom. So that is going to be our delta positive end. And there's a greater electron density around the purple bromine atom, that end of the molecule. So that end of the molecule will be delta negative. So here's two ways that the molecule of bromine, which is essentially overall non-polar, ways in which this can become at least temporarily polar, in such a way that it can then react with the alkene, because we need it to have a delta positive charge for it to act as an electrophile. So either the repulsion of the shared pair of electrons by the carbon-carbon double bond as it approaches, that's the first thing we looked at. And the second thing, these are almost two separate ways that it can do it, are molecular vibrations causing instantaneous dipoles, where your molecule becomes slightly positive at one end just by molecular vibrations causing the electrons to move slightly within the molecule. Once it has then got that at least temporary dipole within the molecule, then it's ready to act as an electrophile and proceed by the mechanism that we saw at the top of the page. So the reaction we've just looked at is actually the basis of the test for alkenes, and can be used to distinguish between alkanes and alkenes. So the reason why bromine can react with alkenes is because they are unsaturated, and so the bromine can add across the double bond, as we've just seen on the previous page. But because alkanes are saturated, they have no effect on bromine, so they can't react with bromine, and there's no more room for any extra bonds. So alkenes do react with bromine because they're unsaturated. Alkenes don't react with bromine because they are saturated. And the effect of this is that when the bromine adds to alkenes across the double bond, a colourless molecule is formed, a colourless substance is formed. Therefore, the original colour of bromine will be removed. We say it decolorizes bromine. Now, it depends what form of bromine that you start with. Bromine liquid is red-brown, but normally we react this with bromine water. So we usually describe the test as shake with bromine water, and you'll see what that means in a second. I'm going to show you a practical video of me carrying out this experiment. So you would get a boiling tube and a small amount of your alkene, pour in a small amount of bromine water, put a stopper on the top and shake them together to allow them to mix and react. If we are reacting it with an alkene, then the bromine water, which starts as orange, so the colour of bromine as a liquid, just as the element itself, is red-brown, but when we make up an aqueous solution, it's orange. You can also say yellow or brown, but orange was the colour that we learnt back in our halogens topic of an aqueous solution of bromine, so we'll stick with that. So shake with bromine water, and it will change from colour orange to colourless with an alkene, but not with an alkene. Let's have a look at the structural formula for this reaction so that we can see why this proceeds with alkenes and not with alkenes, and then I'll show a video of me doing this reaction. So when an alkene reacts with bromine, as we have seen in the previous page with our mechanism, the bromine adds across the double bond. So the double bond breaks, and it uses then the extra room for bonds to form a bond with each carbon atom. So one bromine atom attached to each carbon atom. So this is just general equation using the example of ethene, but each double bond, carbon-carbon double bond, will react with bromine in this way. And bromine water, as we said, is orange, but the product that we form is colourless. So this is the test for alkenes, in that if we shake bromine water with an alkene, it will change the bromine from orange to colourless. In other words, it will decolorize bromine. If we look at the equivalent alkene, which is ethane, and we try to react it with bromine, nothing will happen. So this reaction cannot happen because the alkene is already saturated, as we highlighted in the paragraph above. It's already saturated. There's no more room for carbon to make any other bonds with the bromine atoms, and therefore bromine can't add to the alkene molecule, and so therefore no reaction happens, so the bromine remains orange. So therefore, this is used as a test between alkenes and alkenes. If you had two, say, colourless liquids, you didn't know which was the alkene, which was the alkene. This is a test that you could do to distinguish between the two. Add a bit of bromine water to each and shake them so they react together and mix. And the one that decolorizes the bromine will be your alkene. The one that remains orange will be your alkene. So I'm going to show you a quick practical video of me carrying out this experiment so that you can see the observations of this reaction for yourself. So girls, in this video I am going to show you one of the reactions of alkenes, the reaction with bromine, and we can also use this as a test between alkenes and alkenes. As we learnt, alkenes are saturated hydrocarbons, so they just have single bonds, they have no double bonds, and they're totally saturated with hydrogen atoms. But with alkenes, they have double bonds between the carbon atoms, not all of them, just at least one carbon-carbon double bond, and so they are unsaturated. So what we'll see is that they can react with bromine water. So what I've got here are an alkane and an alkene, very similar. We've got cyclohexane, that's an alkane, and we've got cyclohexane, and that's an alkene. So what I'm going to do is measure out roughly 10 millilitres of each into each of the boiling tubes. Then I'm going to add bromine water and see what happens with each. So let's start with the cyclohexane. And we have to do this in a fume cupboard mainly because of the bromine water. So roughly 10, doesn't have to be exactly the same. I want to make it as fair as possible, but doesn't have to be exactly the same. I'll put that in my first boiling tube. So that's our cyclohexane. And then measure out roughly the same of the cyclohexane. And pour that in the second boiling tube. So you can see these are colourless liquids at the minute. Okay. And what we're going to do is add some bromine water. So let's have a look at bromine water. Okay. So remember, all of our halogens are toxic, and so that's why we want to use a fume cupboard to make sure I'm not breathing in any of the vapours that are coming off this. So I'm going to add 10 millilitres of bromine water to your alkane. And you can see the bromine water was an orange colour, and we'll do the same, we'll add that to our alkene as well. Just about have enough, just short of 10 mils there in our bottle, but we'll add that to our alkene. So you can see it's orange to start off with, and add that to our alkene. Now this is an aqueous solution of bromine water, so you can see that we're forming two layers initially, because our alkane and our alkene are organic molecules, and they're non-polar molecules because there's just carbon and hydrogen in these molecules. Bromine water is an aqueous solution of bromine water, and so therefore they don't mix very well. Okay, they're in sort of, we've got a non-polar molecule mixed with an aqueous solution, and so they don't mix very well. So we've got to shake them together. So let's see what happens when we shake our alkane, with bromine water. So you can see when we shake it with bromine water, the colour remains orange. There's no change, and you can see our different layers forming again then if we leave it to settle. But there's no change in colour of the bromine water, it remains orange. But let's see what happens when we shake it with the alkene, the cyclohexane. So let's shake it there, and you can see that the solution has changed to colourless. So the orange colour of the bromine water has disappeared. The colour change is from orange to colourless. And that shows us that alkenes can react with bromine because they are unsaturated, but alkanes cannot react with bromine because they are fully saturated. So there's no room for the bromine atoms to add on to the alkane molecule, whereas bromine can add across the double bond in our alkenes. And therefore we can see a reaction has happened, and the product that we have made is colourless. So the bromine water loses its colour when it's reacted with the cyclohexane and has added across the double bond. So this can be a test for between alkanes and alkenes. So if you had just an unlabelled bottle and you knew one was an alkane, one was an alkene, you could carry out this test, and the one that changes bromine water to colourless will be your alkene. So what I would like you to do now is to try some of the structural equations and mechanisms for yourself. As I said, the electrophilic addition reactions that are mentioned on your specification, the specific ones you need to know, are alkenes reacting with chlorine, bromine, hydrogen chloride and hydrogen bromide. So we have done the bromine and hydrogen bromide examples on the previous pages, and now I'd like you to complete the structural equations and mechanisms for the reaction of an alkene, and we're just using ethene as our example in each case. So part C. The third example is on page 17, the reaction of ethene with chlorine. And what you'll see is that is an identical mechanism as with bromine, but just with chlorine instead of bromine. And then hydrogen chloride with ethene is over on page 17. And again, that's an identical mechanism to hydrogen bromide reacting with ethene, but just obviously with a chlorine atom instead of the bromine atom. So give those a go now, and then you can check the completed notes for your answers. But essentially, check your previous mechanisms; they're going to be exactly the same. But do try to maybe look back to the previous mechanisms, and learn them. And then try your best to do it without your notes for these examples, just so that you have a bit of practice. Perhaps maybe you want to do it on scrap file paper, check with the previous mechanisms and then copy it into your notes. But give this a go. Again, remember the format of the mechanism is exactly the same each time. Just check your curly arrows that they're going the right direction. Check that you've got your delta charges on your molecules, the full charges at stage 2, and the lone pair on the part of the electrophile that's broken off as well. So have a go at those two examples of structural equations and mechanisms, the reaction with chlorine and the reaction with hydrogen chloride.